So now that we know how to determine the shapes of molecules, we can take it one step further and we can determine the polarity of molecules. By this we mean, can you determine whether the molecule is polar or is it nonpolar? And if it's polar, is it more polar than another molecule? We can make comparisons. And this will be an important tool for us to use for predicting behavior of these molecules later down the road. So eventually we'll use this in subsequent chapters, but for now we're just going to learn how to determine if a molecule is polar or not polar. The polarity is going to come from those shapes. So we had learned back in chapter 9 whether or not a bond is polar. We talked about bonds being very polar. It's so polar that we call them ionic, down to being not polar at all because it's two atoms that are exactly the same electronegativities connected to each other. But that was just about the bonds of the polarity. We're going to take that bond polarity and combine it with the shapes of the molecules to figure out whether or not it is polar. Now, what we're going to learn how to do is use a vector. A vector is an arrow and it has a couple of features to it, but this vector is going to be written in such a way that it shows those bond polarities that we learned about in chapter 9. So what does a vector have? It's got two components. It's got a direction, and that direction will be in the three-dimensional world of the shape of that molecule, and it has a certain length. The length is going to be dependent upon how polar that bond is. It's a relative thing. It's not like you draw it 2 centimeters if it is polar to this extent, and you draw it 3 centimeters if it's polar to this extent. It's just once you draw the molecule, if you have one bond that's polar than another bond, you'll draw its vector a little bit longer than the other one. And of course it's going to have a direction, and that direction is going to go in towards the direction of the more electronegative atom. Okay, so we're going to use as an example a very basic molecule consisting of 2 atoms there. We're going to look at HF. So here is a electron map of this HF molecule. The blue is representing the area that is electron poor, and the red is representing electron rich. Now what do I mean by electron poor and electron rich? Remember when we talked about HF and that bond polarity, we knew that fluorine was more electronegative, and being more electronegative, it has the ability to draw the electron density towards the fluorine end and away from the hydrogen. So we could represent that molecule as HF. Now that little arrow above it is the vector I'm talking about. That vector is pointing towards the more electronegative atom and away from the hydrogen. And we've made a little plus sign over the hydrogen to represent that it is partially positive. Now we had kind of written it this way before, with the partial positive and the partial negative to represent those two, but that is a fine way to represent that molecule, partial positive, partial negative. But we're practicing with the vectors here. Okay, so that vector we see has the positive end and has the negative end. The negative end is where the arrowhead is. The length of the arrow would be a magnitude of how polar this is. Now this is quite a polar bond. And so I've drawn a long arrow. Well, you don't know that it's a long arrow, but we'll say it is, okay? So that's a long arrow, okay? Now, this is a very key statement, so we probably ought to put a star next to it, all right? This is a key statement here. If you have a molecule and it has only one bond, like HF has, then if the bond is polar, the molecule must be polar. End of story. However, we have an awful lot of situations where we have more than one bond and we have to figure out what to do. So for molecules that aren't diatomic, there's not just 2 atoms, there's more than 2 atoms, we have to do a little bit of work. We can have situations where the bond is polar, but the molecule is not. Now, if all the bonds are nonpolar, the molecule is going to be nonpolar. End of story. But if a bond is polar in a molecule, the molecule is not necessarily a polar molecule, and we're going to see why. So in order to determine if a molecule is polar, there's a series of steps we're going to have to follow. The first step that we're going to have to do is determine the molecular geometry. Now remember, to do that we have to back way up and start doing a Lewis structure, and we had to take that Lewis structure and we had work to do to come up with that geometry. But once you have the molecular geometry and you draw out your shape, The next thing that you're going to do is you're going to start adding those vectors in. You're going to draw one vector for every bond in that molecule. And you're going to make that arrow point away from the least electronegative atom towards the most electronegative atom. And you're going to do that all over that molecule. The third thing you're going to do is you're going to add those vectors together. And we're going to talk about adding vectors as we go through here. As you add those vectors, sometimes the vectors point in exact opposite directions and they cancel each other out. Sometimes they're both pointing in one direction and it's a summative thing. They add together. So it just depends on which way the vectors are pointing in order to add them together. Now, we're going to learn some quick things to look for where you don't have to actually draw out the vectors, and as soon as you see this, if you memorize a few things, you can save yourself some time. That's the only time I like to memorize things, is when it saves me time. But you could always do these steps if you know how to add your vectors. Okay, so how do we add vectors? First of all, if vectors are in the same size, and they're pointing in exactly opposite directions, then they will cancel each other out. Now, when I say they're pointing in exactly opposite directions, I want you to understand what I mean. Okay, so the same size. We're going to pretend like these two arrows that I'm drawing are exactly the same size. The best I could do. Okay, they're pointing in exactly opposite directions. They will cancel each other out, and if those were the only two vectors in my molecule, then they would cancel each other out, and the molecule would be nonpolar. But they don't have to be pointing in exactly opposite of each other in the same line. You could have a vector here pointing in this direction and the exact same vector length pointing in this direction somewhere else, but it's exactly the opposite direction. Those would cancel each other out. So that's the simple rule for vectors. The second one is if the vectors are parallel, by the way, these are parallel but pointing in opposite directions. If the vectors are parallel and pointing in the same direction, then they're going to add the lengths together. So let's see an example of that. I've got this one. Maybe it's some bond in there that's pointing this direction, and then I have another one for a bond pointing in this direction. I will take the end of the one to the point of the other, and that would be the sum, assuming that I didn't have a gap there. The sum of those two things would be the vector of adding those together. And once again, they just have to be parallel. They don't have to be in the exact same line. So I could have somewhere in a molecule one pointing here and somewhere else in the molecule pointing here. They are absolutely parallel, pointing in the same direction. And so the length of this plus the length of this would be the length of the vector that is the sum of those two. Okay, so that's the second one. The third one is if vectors point in the same general direction. What you would do, and let's read what it says here, you keep the angles of the vectors set the same. So whatever angle that they are positioned at, you're keeping those the same, and you're moving it so the tip of one arrow is touching the tail of the other arrow. I'm going to show you what I mean by that, okay? The vectors that connect the tail of one to the tip of the other is the sum. All right, so let's say I had somewhere in the molecule a vector pointing in this direction, and that's, pointing up. And I have one somewhere else in the molecule that's kind of going off in this direction, okay? So those are my two vectors. I'm going to move this vector and not change its angle, so I can't rotate it at all until I keep it exactly the same length and put the tip of the one and the tail, what does it say there? Keep angles of the vectors the same and connect the tip of the one arrow to the tail of the other. So I'm going to move this up like this, okay? So it's going in the same exact angle, it's exactly the same length, and that is that vector having been shifted to there. All right? And so what we can do then is connect the tail of this one to the tip of that one, and this right here is the summation vector. That's how you sum them and get a length. Now, you really don't have to go to that level of extreme to do our work. What we can know, and this will be good enough, if we have a vector here and we have a vector here going off in these directions, the summation vector will be in between them, okay? And that will probably be all you need to know. Notice how my summation vector was in between those two. So you have two vectors, the sum is going to be in there. So when we add those together, they are no more, and we have a polarity going off in this direction. Okay? So we're going to look at some examples and practice this process, okay? So what do we do first? We need to know the shape of the molecule. Well, to know the shape of the molecule, we need to do a Lewis structure. So to do a Lewis structure, we know that carbon is the central atom, okay? And the oxygens are on either side. We have to count our valence electrons. Carbon has 4, and each oxygen has 6, so there's 2 times 6. Now, where am I getting those numbers? Off the periodic table, right? Valence electrons. So 6 times 2 is 12, plus 4 more is 16. And I have 16 electrons. And just as a review of our Lewis structures, we'll start with single bonds. 2, 4, then we go to the outside atoms and give ourselves 8 electrons until we get up to 16. 2, 4, 6, 8, 10, 12, 14, 16. Then I have to stop. I know that my carbon is not yet happy, so I'm going to shift. So I'm going to take these electrons away here and shift them to there. I'm going to take these electrons here and shift it to here. And now every atom has got the right number of electrons, and that's a good Lewis structure. So then we're ready to do shape. To do shape, we look at our central atom and we see that it has 2 legs. Two legs, meaning electron groups, are trying to get as far away from each other as they can go. Therefore, it is a linear shape. So the way I've drawn it is linear, and so we'll just use that in my diagram here. Now I'm ready to put in my vectors. To put in my vectors, and I'll change colors to put in my vectors, I want to go to the more electronegative atom, have my arrow point in that direction. And so oxygen is more electronegative than the carbon. So I will put a vector pointing from the carbon to the oxygen. I will give it a length. I have chosen this to represent the polarity of that bond. Now what I know about this bond is it's exactly as polar as that bond, but it's going to go in the opposite direction. So here is a vector pointing in exactly the opposite direction. It's the exact same length. So this molecule is a nonpolar molecule. So this would be a nonpolar molecule, but we would say it has polar bonds. So the bonds certainly are polar because the electronegativity or differences occur there, but the molecule is nonpolar for the reason that those would cancel each other out. Okay, so this is, of course, the image that I just drew, but on the right-hand side we see the electron density map of that. What we'll see is we still have the blue area where it's a little electron deficient, and that would be where the carbon is. We see the red, it's not too red there, but the area towards the oxygens where it's more electron rich, but there isn't a plus end and a negative end to this molecule. There's kind of a positive center and negative ends, and you don't have a polarity unless one end is positive and the other end is negative. So let's do another example. These two molecules, NH3 and NF3, will be very similar in a lot of ways, but something about their polarity will be different, and we'll see that as we go. So let's do NH3 first. Now for speed, I'll just go right ahead and draw the Lewis structure. Here's my Lewis structure. Knowing that I would have counted electrons to do all that. See, I have 4 legs, so I know that I have a tetrahedron electron geometry. So I will draw a tetrahedron, okay, 2 coming out towards me, going back away from me. I'll put the lone pair here. I'll put a hydrogen here, a hydrogen here, and a hydrogen here. Okay, so that's what NH3 would look like. How would NF3 be different? Well, it wouldn't be much different. When it comes down to it, what we'd have is a electron pair on the nitrogen. We would have these 3 bonds still, but there would be fluorines on each of those locations. So now we're ready to put in our vectors. Our vectors go from the least electronegative to the most electronegative. Now nitrogen is more electronegative, okay? So I would draw a vector towards the nitrogen. I would draw a vector towards the nitrogen. I would draw a vector towards the nitrogen. Now these are all 3 pointing in a general up direction. We also will always have a vector for the nitrogen to the lone pair. Now it's really, we don't know how long to draw that, but there is electron density up here, so we should draw in a vector for that. And we see that all arrows are going from a down to an up position here. So this molecule is polar, and what we would have if we drew a summation of all those vectors, since they're all pointing in the general up direction, is we would have a polar molecule, and we would have a positive down here, and we would have the negative up here, and that's how it would orient itself. But this is a different, because between nitrogen and fluorine, fluorine is more electronegative. Fluorine is the most electronegative atom on our periodic table, so all of these are pointing in a general down direction. Now I would have a vector for the lone pairs pointing in this direction. It is never going to happen to be the same length as the vectors for these bonds, but there is one pointing in the up direction. But we have a whole bunch pointing in the down direction here, a little bit in the up direction, so this molecule is going to be polar, where the negative concentration is down at the bottom and the positive direction is more up at the top. So the polarity is different because of which atoms are attached, but they're both polar molecules. All right, what else we got on here? Now, this is a very, one of those statements that said if you can memorize a few statements, you can save yourself a lot of time. This little statement says here that if the central atom has one lone pair on it, see what I have here? One lone pair. This is not if it has more than one or more. This is if it has one. We can always say with certainty that it's going to be a polar molecule. So that means that once you've drawn this, if you know that statement in red, you don't have to do all this work. It will always be the case that that thing will make the molecule a polar molecule. It's worth knowing that statement to save you all of this work. All right, let's do the SCN that we see here. All right, so my central atom is the one that we see written in the center here, okay? So the carbon is in the middle. And then we have an S on one side, we have an N on the other side. And the way this molecule looks is actually, all right, like carbon dioxide. It's very similar to carbon dioxide. This is at least one of the resonance structures. Now, one of the things that you need to know about doing this is you don't have to draw all the resonance structures. You don't even have to draw the best resonance structure, but you have to draw a resonance structure. All of the different resonance structures would have the same shape, and so it really doesn't matter. Now, for this one, between carbon and nitrogen, nitrogen is more electronegative. Between sulfur and carbon, the more electronegative one is hard to say. They're very similar. Carbon is up one, so that's higher on the periodic table, but sulfur is to the right of that, which makes it maybe a little bit more electronegative. So these are actually very, very close to the same electronegativity of each other. And unless I look up values, I don't know which way it points, but I know it's not going to be long. It's going to be very tiny and maybe not even enough to register. Whether I drew it this way because I think carbon would be the one that's more electronegative, or sulfur because I thought sulfur was the one that's more electronegative, this molecule with those two vectors is definitely going to be a polar molecule, because regardless of which way this points, it's tiny, it's not going to be the same as this, and this is going to dominate. So this molecule will be a summation vector that will be polar in the direction of the nitrogen. So this molecule, while it's the same shape as that molecule, the same bonding pattern as that molecule, this one is going to be a polar molecule, while that one was a nonpolar, while the carbon dioxide up there at the top was nonpolar. All right, let's do water next. We'll do water in this space over here. Here is the Lewis structure of water. Once we have the Lewis structure, then we can do the shape of water. It has 1, 2, 3, 4 legs. So we have our oxygen in the middle, okay, and we have our tetrahedron arrangement, okay. So there's my tetrahedron. Now I could choose any two of those legs to put my lone pair on, and then I'm left with the other two with the hydrogen atoms. Let's put our lone pair here and another one here, the hydrogen here and a hydrogen here. So there are the atoms with my geometry. Now, we said that when it has one lone pair, it will always be polar. But we can't say that when it has two lone pairs. Sometimes it will be polar and sometimes it won't be polar. So we need to draw our vectors. Between hydrogen and oxygen, oxygen is more electronegative. So I draw it towards the oxygen, And we have vectors heading off in the direction of these lone pairs. Okay? All of these vectors are pointing in the same general direction, in this direction. And so that could be my summation vector. The one that I've drawn right here be pointing in this direction. So we have the negative over here. We have the positive end over here. This molecule is polar. One way to think about this summation vector, and really what you just need to be able to say at this point in your chemistry life is this molecule polar or is this molecule not polar? Is this molecule polar or not polar? And if you don't see the vectors canceling, then it's going to be polar. But what you can think about is if each one of these little vectors that I'm drawing in was a tug of war between the central atom and these outside areas, and they were pulling harder in the direction of which way it's pointing, would this molecule get pulled away? And if it gets pulled away, then it's going to be polar. If this were a tug of war and they were pulling exactly as hard as they were pulling, this would not move anywhere. That tug of war would be, I don't know, happening forever and they're not going anywhere. So sometimes it's helpful to think about this as a tug of war between the electronegative ends of that vector, and the way it's pointing is winning the tug of war. And if the molecule would move in a tug of war, then it is a polar molecule. So if this is pulling really hard this way and a little bit more this way, certainly it's a polar molecule. Even if this were in the opposite direction and pulling a tiny bit this way, the molecule would still be traveling in that direction in terms of a tug of war, and that would be a polar molecule. Okay, so we've got our drawing of the water. Let's look at the image that we see here. The image on the left shows the vectors kind of ignoring those lone pairs, and that's one thing that you can realize you can do. You don't really have to draw in the vectors for the lone pairs because it will not, while they do have a vector, it will not affect your ability to come up with polarity. So on the left, they've totally ignored the vectors for the lone pairs, and they've just drawn the vectors for the hydrogen-oxygen bonds, and we see the summation vector in between those pointing up. That tells me that the top of the molecule where the oxygen is sitting is partially negative, and the bottom down where the hydrogens are is the partially positive end. So this is a polar molecule. So we go back to that statement in red that we say, it says that the central atom has one lone pair, it will always be polar. This is a situation where we have two lone pairs. We cannot say it will always be polar. We will need to draw the geometry in order to determine if it's polar or not. But I want you to know with certainty, so that you do not have to go through this every time for water, is that water is forever and always polar. We use it so often as examples. Ought to have a verb in there. Water is polar. We use it so often in examples that you will run across it all the time, and it would be no fun whatsoever. Sorry for all that distraction. It would be no fun whatsoever to do that every time. Keep in mind that water is polar. It has two lone pairs, but having two lone pairs is not what makes it polar. It's the geometry it comes across, and there are times where the lone pairs are going to cancel each other out vector-wise, and it's going to be a nonpolar molecule. But remember that statement. So we need to do some more examples. But before we do, let's look at this next statement, because this is another statement that if we can just keep it memorized, we're going to be able to save ourselves a lot of time. Now let's see what it says there. If you take a geometry and it has no lone pairs, that's one thing. So here is a shape where it has no lone pairs on the central atom, and all the legs, and what am I calling the legs? These are the bonded atoms to it, are the same atoms, then that molecule is always going to be polar. Whether it is linear or any of our other geometries. So right over here in this space that I have, I'm going to consider all my other geometries. We've got the linear. If we have no lone pairs and it's linear, it is going to be nonpolar as long as the external atoms are the same. Other shapes that we have is the trigonal plane. Remember, trigonal plane like BCl3 is, if you want to look back in your notes at it. These vectors, while if they're all the same atoms, if we consider that tug of war and they're pulling off in these three directions equally, that molecule's not going to go anywhere, right? So that is another example of a nonpolar molecule. The next shape would be a tetrahedron, okay? So if all the legs are the same atom and there's no lone pairs and we did a tug of war in those directions, it would be nonpolar. We have a trigonal bipyramid, okay? So we have one up, one down, and the three in the equatorial position. If we're pulling in those directions, it would be nonpolar. And then we have our octahedron. So these are our geometries that we have learned where there are no lone pairs. An octahedron, if all the atoms are the same atom around an octahedron, it'll be nonpolar. So as soon as I've drawn a Lewis structure, if I notice that I have one of these shapes and there's no lone pairs and all the atoms are the same atom, then I know instantly that it is nonpolar without having to do all the vector work that we see right there. So that gives me two always statements. One always that we see here, if all the legs are the same atom of any one of these 1, 2, 3, 4, 5 geometries, all the atoms are the same atoms, it's nonpolar. And the other statement was on the previous slide, if any one of these shapes has one of the legs as a lone pair, it will become polar. We could also, well, I won't say that right now. Let's see what else we have here. I think we'll erase our screen and be right back with you. So let's do some other examples. The next one is BCl3. So if we were going to do BCl3, well, I already told you what BCl3 looks like, but let's pretend like I didn't. BCl3 is boron with 3 atoms around it. So boron, chlorine, chlorine, chlorine. Okay. We count up valence electrons. Boron has 5, plus each chlorine has 7. That gives me 26 electrons. I connected 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's not right. Can I not add 21? Oh, boron doesn't have 5. I'm sorry. Boron has 3. 3, then 21. 24. I knew I did something wrong because I knew I was supposed to stop there. So we have BCl3, and with BCl3 we could shift in, but we know that boron likes to be electron deficient like this. Well, likes to. This is the way it is occurs, with the boron being only 6 valence electrons. But if I had forgotten that, and I had put these in here instead, it wouldn't change the information. I have 3 legs connected to the central atom. I have no lone pairs, so as soon as I see that, I don't have to necessarily draw that. I don't have to necessarily know it's called a trigonal plane. I don't need to know the bond angles. I don't have to draw in all the vectors. As soon as I see that all the atoms are the same and there is no lone pairs, it is nonpolar. Okay. So once this is drawn, I can know that statement. If I don't remember that statement, I have to do all the work to get that. The next one is CCl4. So we do CCl4 just for quickness sake. I will go right ahead and draw the Lewis structure. So carbon is connected to 4 chlorines. This is not the geometry that we see here. This is just a Lewis structure. 4 legs trying to get as far apart from each other as they can go would be a tetrahedron geometry. But I don't have to know that. If I know that if all the atoms are the same and there's no lone pairs on that central atom, this guy is nonpolar. Now when I say it's nonpolar, I'm saying the molecule in both cases is nonpolar. The bonds certainly are polar. Chlorine is more electronegative than carbon. The bonds are polar, but the molecule bonds are polar, but the molecule is nonpolar. Now, when a molecule is nonpolar, there's one other thing that we can say about it, and that it has a dipole moment equal to 0. Mu is a symbol for dipole moment. And if the dipole moment is equal to 0, that is a nonpolar molecule. If the dipole moment is not equal to 0, then it is a polar molecule. Now, you'll never calculate a value for a dipole moment in this class, except for this one. If you determine that it's nonpolar, you can give it a value of 0. In both of these cases, that statement at the top would drive an answer without having to draw in our vectors. So now you're going to try this one. You're going to do the Lewis structure. You're going to, after you do the Lewis structure, if need be, you're going to do a geometry, shape, and vectors, or maybe one of those statements will save you from having to do all that work, but you're going to choose the right answer here. Okay, the bonds are polar, but the molecule is nonpolar. So hopefully you saw, once you did the Lewis structure, and you had these 6 fluorines around the sulfur, when you did the Lewis structure, you should have seen that there were no lone pairs on the central atom. All the atoms are the same. Now, each one of those fluorines have the 6 dots around it, so they have 8 valence electrons. But once you drew that, no lone pairs on the central atom, all the atoms are the same atoms, so you would not have had to draw the shape and vectors. You could have known while the bonds are very polar, the molecule itself is nonpolar. So that's the types of things I would like you to be able to do once you are given a molecule, is to determine if the bond is polar or the molecule is polar or not polar. Now, why would we do this? One of the reasons that we do polarity is to know the properties of these things. And the first little property I want to give you is when you have 2 liquids and one liquid is polar and one liquid is not polar, then they will not dissolve in each other. Like likes to dissolve in like. Now, what do I mean by like dissolves like? I mean like in terms of polarity. Oil is a nonpolar substance. It's a hydrocarbon that does not have a polarity. Water, however, is very polar, and I told you need to remember that statement. Water is very polar, and we've heard the adage that oil and water don't mix. It has everything to do with the polarity of those molecules. Why would they not mix? It's not because they hate each other, but the polar molecules are like little magnets. And if you had a bunch of marbles in a glass jar and half of them were magnetic marbles, all the magnetic marbles, if you shook it up a little bit, would find each other and they would just hang out together. So those polar molecules interact very strongly with other polar molecules. And the positive end of one molecule will be attracted to the negative end of the other molecule. So those little magnetic particles, those polar molecules, they clump together. They're going to exclude all the non-magnetic particles, and that is why these things do not mix. Now, we will learn other reasons to study whether a molecule is polar or nonpolar when we get into the chapters on solutions, when we get into the chapters of the solid state and the liquid state. But for now, that's the only thing that you're going to be able to use this information for, is to decide whether or not 2 liquids would easily mix together or not mix together based upon their polarity.